morning. So today we'll see some problems on this first chapter on network theorems. So first we'll see the problems related to the Thevenins theorem. By using the Thevenins theorem, we are asked to obtain the Thevenins equivalent circuit and to find out the current through the load resistance iron. So here we have the problem, first problem. So using Thevenins theorem, determine the current flowing through the load resistance iron of this network. This network consists of a source of EMF of 36 volt, a resistance R1 of 3 ohm, R2 of 4 ohm, R3 of 6 ohm, and the load resistance RL is connected across the terminals A and B having the value 8 ohm. So here you are asked to determine the current flowing through this load resistance RL. Say I is the load current. So by using the Thevenin theorem, we have to find out the current flowing through this load resistance. So first, what we need to do is we have to first Theveninize the given network. And as we have discussed earlier, the Thevenizing a network consists of a 4-step procedure. In the first step, what we need to do is we have to remove the load resistance from the terminals A and B such that the terminals A and B are open circuited. Remove RL from A and B. So after we remove the load resistance from terminals A and B, the network we get is of this type. These are the open terminals A and B. This is the resistance R1, this is R2, this is R3, and this is the source of omega E. So, in the first step, we have to find out the value of VTH or VOC. The open circuit voltage measured across the terminals A and B gives the value of VTH. So, in order to find out the value of VTH or VOC across terminals A and B here, we must know the current flowing through this resistance R3. To find the current flowing through this R3 is nothing but the total current I drawn from the source. So when the terminals A and B are open circuited, this resistance R2 goes out of the circuit and only R1 and R3 remain in series connected across the source of EMF E, so that the current I flowing drawn from the source is equal to E upon R1 plus R3. So this is equal to E is 36 volt divided by R1 is 3 ohm and R3 is 6 ohm. So 36 divided by 9, so it works out to be 4 ampere. So the total current drawn from the source is equal to 4 ampere. So this current of 4 ampere will flow through this resistance R3, and when this current of 4 ampere flow through this resistance R3, whatever the potential difference that is produced across R3 is nothing but the open circuit voltage across the terminals A and B. So this R3 is 6 ohm resistor, therefore VOC, that is nothing but VAB, is equal to VB across R3, and this is equal to I into R3. So I is 4 ampere multiplied by R3 is 6 ohm. So potential works out to be 20 volts. the potential difference across the terminals A and B works out to be equal to 24 volts. And this open circuit voltage across the terminals A and B is nothing but VTH. So VTH is equal to VTC is equal to 24 volt. So we have first, in the first step we have found out the value of VTH. So this value of VTH we must remember. Now in the second step we have to find out the equivalent resistance of the circuit, that is the value of RTH or R equivalent, and to find out the value of VTH, RTH. So VTH is equal to 24 volt. You note here. So in the step 2 we have to find the value of RTH. So step 2 is, what we need to do is we have to kill the source of EMF for its EMF, retaining its internal resistance in the circuit. So the source of EMF, in this case no internal resistance is mentioned here, so we can consider the internal resistance of the source is 0. So this branch is like this. Here we have the resistance R1. Kill source of EMF for its EMF and find equivalent resistance when viewed backwards from A and B. So the network will take the form. This is the first patch, the resistance R1, the resistance R3, the resistance R2, and the open terminals. So this is R1, R2, R3. And when you view this network backwards from the open terminals A and B, when the source of EMF is killed for its EMF, retaining its internal resistance in the circuit gives the value of R equivalent, and this R equivalent is nothing but the value of RTH. So this R equivalent, when we view this network backwards from the open terminals A and B, it appears to us that the equivalent resistance of the circuit is the series combination of R2 and the parallel combination of R1 and R2. So it is R1, R1, R2. This is the equivalent resistance of the network when viewed backwards from the open terminals A and B. So this is nothing but equal to R2 is 4 ohm plus R1 parallel R3 is R1 R3 upon R1 plus R3. R1 is 3 ohm multiplied by R3 is 6 ohm divided by 3 plus 6. So it works out to be 4 plus 80 divided by 9. So it is 2. So 6 ohm is the value of R equivalent. Therefore, RTH is equal to 6 R equivalent, and this is equal to 6 ohm. So we have obtained the value of VTH and RTH. So once we get the values of VTH and RTH, now the network to the left of the terminals A and B can be replaced by this Thevenin equivalent circuit. So what will be the Thevenin's equivalent circuit then? In the third step, we can find out the Thevenin equivalent circuit, and hence the current will be the load resistance. So the step 3 consists of finding the value of I. So So state 3 will be Thevenins equivalent circuit and find the value of I. So the network to the left of the terminal C and B can be replaced by the series combination of VTH in series with RTH or RIN. This is VTH. So these are the terminals A and B, and to the right of the terminals E and B, we can again connect the load resistance RL. We can again reconnect the load resistance RL to the right of the terminals E and B, and now we can find out the current flowing to this load resistance RL as IL is equal to VTH divided by RTH plus RL. RTH is the internal resistance of the source and RL is the value of the load resistance connected to the right of the terminals A and B, so that the total resistance of the circuit becomes RTH plus RL, and the EMF of the source is VTH. So the current flowing to this load resistance RL is given by IL equal to VTH upon RTH plus RL. So using the values of RTH, VTH and RL here. So VTH is 24 volt divided by RTH is 6 ohm and RL is 8 ohm. I think yes it is. RTH is 6 ohm and RL is 8 ohm. So this is equal to 24 by 40. So 24 by 40 works out to be equal to IL works out to be equal to 1.71 ampere. So the current flowing to this load resistance RL of the given network works out to be equal to 1.71 ampere. So that is how we can Theveninize the given network and find out the current flowing through the given load resistance RL. So this is the first problem. So let us see the second problem. Using Thevenins theorem, we have to find the current flowing to this load resistance. Current of the network, say like this. So this is R1, R2, R3, R4. R1 is 4 ohm, R2 is 12 ohm, R3 is 8 ohm, R4 is 4 ohm, and the load resistance RL is connected between the terminals B and D. And the value of this load resistance is going to be 10 ohm. So the source of EMF has the value of 48 volt. The source of EMF is of 48 volts. So in this network, you are asked to find out the value of the current flowing to this load resistance R. Now, in order to obtain the current flowing to this load resistance, first what we need to do is we have to remove the load resistance from the terminals A and B. In this case, it is B and D, and find out the open circuit voltage across the terminals B and D. So, once in the step 1, what we will do is remove RL from B and D and calculate open circuit voltage across the terminals B and D. So, if we remove the load resistance RL from the terminals B and D, the network we get is of this type. Source of EMF. This is the terminal A, B, C, and D. This is R1, R2, R3, and R. So the terminals B and D are open circuit. The load resistance is removed from the terminals B and D. So we get this network. So here we have to measure the open circuit voltage across the terminals B and D. So to obtain the open circuit voltage across the terminals B and D, what we need to do is in this circuit, first we have to find out the potential at the point B with respect to C. We have to find out the potential at the point B with respect to C, and knowing the potentials at the points B and D with respect to C, then we can find out the potential difference across the terminals B and D. And this potential difference across the terminals B and D is nothing but the open circuit voltage across B and D. And this open circuit voltage is nothing but the value of VTH. So, let I1 is the current flowing through this first branch ABC. This is I1, and the current flowing through the branch ADC is say equal to I2. Now, when this current I1 flow through the branch ABC of this network, certain potential drop will be developed across R1, certain potential drop will be developed across R2. And since this series combination of R1 and R2 is connected across the source of EMF, the sum of the potential drops across R1 and R2 must be equal to the value of source of EMF E. So, equating this, we get the expression R1 is 4 ohm, so it is 4I1 plus R2 is 12 ohm, so it is 12I1 is equal to 48. It is equal to E is equal to 48. So 4I1 plus 12I1 works out to be equal to 48. So this gives 16I1 equal to 48, and it implies I1 to be equal to 48 by 16. 48 upon 16 ampere. So I1 works out to be equal to 48 by 16 I1. So if this is the current flowing through the resistors R1 and R2, then what will be then we can calculate the potential of the point B with respect to the point C. This potential of B with respect to C is nothing but the potential drop across the resistors R1. Therefore, potential of V with respect to C is PD across R, and this is equal to I1 into R, and I1 is 48 by 16 multiplied by I1 R2 is 12. So this is so this works out to be 36. It works out to be 36. So the potential at the point B with respect to C works out to be equal to 36. So then we can find out the potential at the point B with respect to C. For that purpose, we must find out first the current flowing through this branch ADC, and then finding out the potential drop across R. So for the branch ADC, we can write R3 is 8 ohm, 8 I2 plus R4 is 4 ohm, so 4 I2 is equal to 48. So this is 12 I2 is equal to 4 ohm. So this implies I2 is equal to 4 and I2 is equal to 4 ampere. So if this current I2 of 4 ampere flow through R4, the potential drop across R4 is equal. Therefore, potential at B with respect to C is PD across R4, and this is nothing but equal to I2 R4. So I2 is 4 ampere multiplied by R4 is 4 ohm. So it works out to be 16 volt. So the potential at the point B with respect to C is 36 volt, and the potential at the point D with respect to C works out to be equal to 16 volt. Therefore, the potential difference across the terminals B and D is nothing but equal to the difference between these two voltages. Therefore, PD across B and D is 36 minus 16. So this works out to be equal to 20, and this is the fact the value of POC. So POC is equal to 20 volt, and as per the definition, the open circuit voltage across the terminals B and D is nothing but equal to the value of VTH. So this is the value of VTH. So we have obtained the value of VTH to be equal to 20. So over here, this is the first step. Now in the second step, what we need to do is we have to fill the source of EMF for its EMF, retaining its interresistance in the circuit, and find out the value of the equivalent resistance of the network when viewed backwards from the open terminals B and D. So for that purpose, what we need to do is we have to kill the source of EMF. Step 2 is kill source of EMF or this EMF and calculate the value of R current when this network is viewed backwards from the open terminals B and D. So this network then can be simplified and expressed like this. This network can be redrawn like this. This is nothing but equal to here we have this is a short circuit across B and C. So this is A and this is C. This is A terminal. This is terminal C. So this is B and this is D. So here we have the resistance B, C. This is D. This is R1. Between B and C we have R2. Between A and D we have R3. And between B and C we have R4. So like this. And this is A and C are short circuited. We have removed the battery from the network. So A and C are short circuited, and when this network is viewed backwards from the terminals B and D, what is the resistance of this network? And that is the value of R equivalent. So this is the R equivalent. So what do we observe here? Here, when we view this network backwards from the open terminals B and D, it appears to us that the two parallel combinations are connected in series across the terminals B and D. So the first parallel combination is of R1 and R2, second parallel combination is of R3 and R4, and these two parallel combinations are going to be connected in series across the open terminals B and D. So therefore R equivalent works out to be equal to R1 parallel R2 plus R3 parallel R4. This is the equivalent resistance of the given network when viewed backwards from the open terminals B and D. So using the values of R1, R2, R3, R4 here, we get R1 is 4 ohm into R2 is 12 ohm divided by 4 plus 12 plus R3 is 8 ohm, R4 is 4 ohm divided by 8 plus 4. So this works out to be 48 divided by 60 plus 32 divided by 2. So this is equal to T plus 32 by 12 is 8 by 3. So R equivalent works out equal to 5.664. R equivalent is 5.66 ohm, and this is given to the value of RTH. This is nothing but the value of RTH. So RTH is equal to 5.66 ohm. So once we know the values of VTH and RTH, now we can draw the Thevenin equivalent circuit, so that the Thevenin equivalent circuit becomes, so step 3 is Thevenin's equivalent circuit is VTH in series with RTH connected across the terminals B and D, and again if we reconnect the load resistance RL to the right of the terminals B and D, we will now current flowing through this load resistance I. So here we have VTH equal to 20 volt and RTH equal to 5.66 ohm and the load resistance RL is of 10 ohm. So the load current IL becomes equal to VTH divided by RTH plus RL. So VTH is 20 volt divided by RTH is 5.66 ohm plus RL is 10 ohm. So this is equal to 20 divided by 15.66. So this is or this is nothing but equal to I am what's equal to 1.277. So the current to this load resistance I will work out equal to 1.277. So that is how by using the Thevenin theorem we can obtain the values of the current flowing through the load resistance. So these are the two problems for your understanding, showing the application of the Thevenin's theorem. So you can practice some more problems. So we will close in this video, and next video we will see the problems on Norton's theorem. Okay, thank you.